So, welcome to the tutorial session for week 4. So today we'll be clearing doubts regarding the week 4 lectures, which are uh, related to Bayes theorem and Bayesian networks. So you can go ahead and post your questions in the chat, or you can ask your questions. So you can also ask any question from the lectures if you have any, or if you have not gone through this. Okay, so Adil is asking, will you explain the cancer prediction example taught in the Bayes theorem? Okay. So, okay, let me share my screen. So, first of all, let us look at the Bayes theorem. So, what does it say? Suppose we have some hypothesis, and we want to predict the probability of that hypothesis given the data that we observe. And this is written as probability of the data given the hypothesis, probability of the hypothesis by probability of the data. So this is said to be the prior, this is said to be the evidence, and this is a likelihood function. Likelihood. Yeah. So in the cancer example that was discussed in the class, we were given that so in the cancer example, we were given that
Sir,
yeah.
just one question.
Yeah.
I think likelihood is a probability of data given hypothesis, the top one. You interchanged evidence and
Yeah,
likelihood.
yeah, 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 sure. Sorry. Yeah, you are right. Yeah, I mistook it. Yeah, yeah. So, we are given that given we actually have cancer. What is the probability that uh, our test results gave us positive? We are given some probability. Say it was, I think, accurate up to 98% of the time. So given the given we don't have cancer, what is the probability that we given we don't have cancer, what is the probability that it gave us positive? I think it was some 0.97 or something. And overall, we had this. What was the probability of having cancer? And it was I don't know, some value like this. I think I'm not sure about the values, so I'm just guessing. So here, what this peak answer says that this is the prior knowledge that we have. So that means out of all the population, what percent of the population actually has cancer? So suppose we get a test that says the test results are positive. So given that our test results are positive, we want to know what is the possibility that, or what is the probability that we actually, what is the probability that we actually have, or the person actually has a cancer. So now we plug in what is the prior knowledge. So in general, what is the probability of having cancer? So we'll have P of cancer. Then we plug in, given the cancer, what is the, given that the patient actually has cancer, what is the probability that the test results return positive? So that will be your this quantity. What is the likelihood of the test results returning positive if the patient actually has cancer, divided by the patient having cancer, uh, cancer. So divided by probability of the this is a normalizing factor, having cancer and actually returning positive, or probability of having cancer and getting a negative. So this is what we get from the Bayes application of the Bayes theorem. Uh, so it so Adil, this is what we do by putting in these formulas. So basically, it is your understanding of where to put this probability. So whenever you are given, so if you are given an overall, say, probability, that is the prior knowledge that we have. And given the prior knowledge, what is the probability of what is the this is the posterior probability. Given the prior knowledge, how does your probability changes? So given pH, how does your confidence in your results changes? That is what is given uh, by this Bayes theorem. Is it clear? Is that what you were asking, or is there anything you want me to explain further? So the recordings, so in the this online courses website, if you go to the bottom, I think there are there's a link for getting these recordings. Check. Yeah, there is this panel called problem solving session. You can get the recordings, link to recordings from that.
Hello, sir.
Hello.
The bottom evidence, you made a statement. Can you just confirm once again? I feel it is a probability of cancer multiplied by probability of positive given cancer plus probability of no cancer given probability
Oh yes, yes.
yeah,
Take
no
this.
cancer and the probability of
Doctor this given no cancer. Yes, yes.
plus, right?
Yeah,
Yeah.
yeah. So this is just your all the possible cases. So this evidence just says that out of all the possible cases that the patient has cancer, so what is the uh, number of times he can have cancer out of all the possible cases? So yeah, yeah, you are correct. Yeah. Suvan is asking, can this be represented by a confusion matrix? This cannot be represented by a confusion matrix because in the confusion matrix, you just represent the frequency or the number of times that some event occurs. Like so, suppose we have some say these are your these are positive. Suppose these are your true labels and these are your predicted labels, and yeah, so these are your true positives, these are your true negatives, these are your false positive, these are your false negatives. So this just the confusion matrix just says what is the performance of your model, or mm, how many how much how what is your accuracy, or what is your this precision as you call. But when we go to Bayesian way of thinking, we have this extra term called prior. So these terms are they just work on the frequency of your data. But in Bayesian terms of thinking, we always think about the prior. What is the uh, is my screen not? Is my screen visible? Can anyone?
Yes, sir, visible.
Okay, thanks. Yeah. So in Bayesian way of thinking, you always have to include this prior. So so yeah, you cannot express it as a confusion matrix. Those are slightly different metrics that we have.
Sir, can you please tell about this marker?
Oh, so whenever we talk about Markovian processes, uh, so suppose we have a graph. Suppose this is a graph, and suppose now you are at some node.
Sir, your
Suppose
screen is not visible. I mean,
oh,
whatever you're writing.
data seems to be false. Yeah, suppose we have this graph, and suppose you are at this node, and now you have three chances of either you can go from this to this node, this to this node, or this to this node. Suppose with some probability you go to this node. Now at this point, suppose there is one other node. Now at this point you have some probability of going to this node or this node. Suppose you go to this node. Now you are at this point. Now you see, suppose from going from here to here you had some probability say P1, and from going here to here you had some probability say P2. Now your decision to go from this point uh, the decision to go from this point to this point, it does not depend on your past decisions. uh, so at this point you decided to go from here to here, so this does not affect whether you want to go from here to here or here to here. So at every time step you're only concerned about the decision that you take only one time step before. So this is a Markovian process. This type of process is called a Markovian process, or it is said to be a memoryless sort of process. So when suppose in terms of Bayesian learning, there are a set of events taking place. You are only concerned about the events that took place just one step before, and not the events that took place say 2, 3, or 4 steps before. So that is Markovian process. Is it clear?
Yeah, okay, sir. Thank you, sir.
Sir, sir,
Yes. Yes, go on.
sir, can you just focus on naive base naive conditions?
What do you mean by need-based conditions?
At least is one example of how to decide the probability of an event using naive.
Okay, so suppose we have some data say X, so and it has say n features, right? So these features are like your length, width, height, all those things. And suppose it has some output y. Suppose there are two classes, 0 or 1. Now suppose so one of the main things of this, the reason it is called a naive Bayes is because of this assumption that all of these xi's are independent. So each of these feature is independent, due to which suppose we want to check, suppose 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 we are given some x, what is the probability of y given x. So given a data point, what is the uh, what is the probability of the class. So for that what we do is we write this is equal to probability of uh, give me a moment.
Okay.
Yeah, so we want to find the probability of your output or a class given your input, right? Now by Bayes theorem we know that probability of y given x is your probability of x given y and your prior probability. So suppose you are given a data set with say 100 points, and of these 100 points your 70 of those points are say of class 0 and your 30 are of say class 1. So then we get that probability of uh, class 0 is 0.7 and probability of class 1 is uh, 0.3. So these are your prior steps we have. Now what to do about this likelihood? So this is actually your probability that x1 given this x1 x2 xn given y, and the probability of y, and we know this. So for this, because now we know if two random variables x, suppose not x, suppose your random variables r1 and r2 are independent, then probability of r1, their conditional independence, can be written as probability of r1 and probability of r2. So using this we can say that because we assume that all of these xi's are independent, we will have that probability of x1 given y, probability of x2 given y, and so on, and at last we will have this probability of y. Now we know probability of y, we can get this probability of x1 given y, x2 given y from the data set, because suppose x1 is your, suppose x1 is your color, and suppose we can have that there can be two colors, say blue and green. So this will be like probability of blue given y, probability or probability of red given y, or more specifically, we can say that probability that x1 equal to green given y, and so on. So in this, you can calculate these probabilities by from the data set, and once you multiply this, you will get the posterior distribution of your class given x. So you do this for all the possible classes. So suppose y takes two values 0 and 1. So you do this for y equal to 0, and you also do this for y equal to 1 given x. So after you do this, so your decision, what given a test point, say x test, your class will be the maximum of this and this. So maximum of probability y equal to 0 given x, and probability y equal to 1 given x. Well, not maximum, it is the argmax, that is for which y you are getting the maximum probability. Is that clear?
Yeah, yes, sir. Yes, sir. Thank you, sir.
Sandeep is asking, while training language yk having n values, we only estimate n minus 1 value. Because so overall, for any given point, we know that the probability will sum up to 1, right? So probability of y equal to yk, and if we sum it for all the values of k, this should be equal to 1. So if there are, say, n values of k, once we have the values for n minus 1, we can directly get the remaining value by 1 minus the sum of the rest. So that will give us the value of the rest. So that's why we require only n minus 1. We need to know only n minus 1 terms. Is that clear? So Sonali is asking how to calculate the probability of a node in a Bayesian network. So first of all, we know the events that or know the different events that take place. Like suppose we have some, say, A, we have B, and suppose we have C. So we suppose we know this PA, is at a prior probability. Suppose we know PB. Then we also know that given A and B, we can compute what is the probability of C given A and B. So most of these, so they maintain this conditional probability table. I think I mentioned in the class, conditional probability table. and from this we can know the different values. So let me even give a review of this. So is this screen visible?
Yes, sir.
Yeah. So suppose so this is a slide that has been shared online. So it belongs to Miles Auspeck from University of Pittsburgh. And from this slide, let me show you an example of this belief network. So suppose we have this network. Burglary and earthquake which raises some alarm, and once the alarm is raised, we go to the event whether to call John or call Mary. So we have prior probabilities given. So what is the probability of burglary happening? What is the probability of this earthquake happening? And based on those prior probabilities, we can get these probabilities of this event alarm happening given P and P. So for that case, they mention this type of conditional tables. So here T and F means, so what is the probability of burglary happening? So true, that means it has 0.001 probability of happening, and it has this much chance of not happening. Similarly, we have this prior probability for earthquake. So given that this alarm is dependent on these events of burglary and earthquake happening, so for different events of this burglary and earthquake, we have these different sort of probabilities. Say this says that what is the probability of alarm going on if our burglary is true and earthquake is false. So these are the type of alarm will go on with probability 0.94. It will not go on with probability of 0.06. So given we have this probability table for the event alarm starting, then based on this we have these probability tables for these events. So probability of calling John if alarm turns on is 0.9, or if the alarm does not turn on, the probability of calling John is say 0.05. So in this way, we have we maintain these conditional probability tables, and based on the problem at hand, we can use these probabilities to say to apply to whatever task that we take. Is this example clear? Oh, is my screen not visible? Okay. The example was clear, right? Or do you need more explanation? Yeah, I was muted. Yeah, these events are whenever this Bayesian network is created, these events are given during that time. So using these probabilities, you have to compute the probability of event that you are measuring. So any other questions? Any other topic you need explain? Uh, what do you mean by this? Means there is no solving this model. You need to have a task. So in this example, suppose you want to know the event probability of the event where Mary, where you call Mary. So from that you have to use the probabilities that are given, and then you calculate. Means it depends on your task. You do not solve this model. This is just a representation of the different events that can happen.
Hello, I joined a little bit late. Can Can you explain this? What?
Oh, okay. So I was explaining this example of Bayesian belief network. So here there are four events, right? I mean, there are five events that can take place. So suppose there is a burglary. What is the probability of that alarm? And or there is an earthquake. What is the probability of the alarm starting? And once the alarm goes on, you either call John and Mary. So for that case, we are given this probability. So the network is given this conditional probability table. So that covers all the possible all the possible events that may occur. So say what if the burglary happens, that is true, or what if it is false. And similarly, what if earthquake happens or earthquake does not happen. So based on the on whether these events happen or not, the probability of this alarm going on are different. So let's say the burglary does not happen but earthquake happens. So in that case, your alarm will go off with probability 0.29 and will not with probability 0.71. And similarly, given that this event occurs, what is the probability that you call John or you call Mary? So this knowledge of these events is embedded into this belief network, and given this knowledge, you can so given any task, you can use this information to compute the probability of your event occurring. Say what is the if you ask what is the event that John gets a call given this occurs. So you will use these probabilities to compute the probability of calling John. Is that clear?
Okay, thank you.
Let me give you some. Let me give you an example of this Bayesian way of thinking. So this is Jupyter Notebook Code First in ML, and it has been developed by Jeet Patel, who is a PhD candidate at IIT Kharagpur, and he has designed this notebook. So what do you mean when we say that? What do you mean by this Bayesian thinking? So suppose I tell you where to guess whether Steve is a farmer or librarian. So these are his characteristics. So he's very shy and withdrawn, very helpful, and he's meek and tidy. So if I say this information about Steve, so what do you think Steve is? Whether he's a farmer or is he a librarian? Anyone? So this is a good example of getting to understand this Bayesian way of thinking. So the characteristics of Steve are given as shown in the screen. So would anyone like to guess whether it is referring to whether Steve is a farmer or is he a librarian? Anyone? Okay, Sandeep, can you just give an explanation of why do you think he's a librarian? You can type also. Anyone can take this. So if you think he's a librarian, why do you think, or why is your answer that he's a librarian? Or if he's a farmer, why do you think he's a farmer? Or is there information still? Do you require some more information to make this decision? There is no right or wrong answer. It's just like a small game to have this to learn about this Bayesian way of thinking. Okay, since nobody's asking, okay, okay, Balaji, yeah, you are right that because he needs to be structured, so he may be a librarian because you need people who are orderly and structured to run libraries. But so there is one information still missing. So look at this image. So in this image there are 210 people, and of these 210 people, this green represents the number of farmers, and 10 represents the number of librarians. So given this information, what do you think is more likely? Is Steve more likely to be a farmer, or is he more likely to be a librarian? Or okay, Balaji says by common sense. So when we talk about common sense, so basically we are thinking that in general what we observe is librarians are mostly structured, orderly people, and farmers are not that as structured as these librarians. So, but given this data that only 10 people in 10 people, so suppose Steve comes from a population where only 10 people are librarians and 200 people of them are farmers, don't you think there is a probability that he may be a farmer as well? Because see, so suppose I say that 40% of librarians, suppose I say that 40% of librarians satisfy these characteristics, and say 20% of the farmers satisfy these characteristics. Now, if I go and compute the probability of Steve being a librarian, we get something like 16%. And if we go and compare the probability of Steve being a farmer, it goes up to something like 84 or 85%. So yes, there's a higher probability of him being a farmer. So the gap in our understanding was we did not have this prior distribution. We had the probability of a librarian following these characteristics. We had the probability of a farmer satisfying these characteristics, but we had no knowledge of the overall distribution, or in general what is the prior probability of any of these events occurring. That is why we came to not so correct conclusion that he may be a farmer or librarian. So are you not able to see the chat? I don't know how to control this, but I thought you were able to see chat here. Yes, now we we can say high probability that he is a farmer. So this is actually taken from so I am posting a link in the chat. uh, I think it should be visible to all. So this example has been taken from YouTube channel called Three Blue and One Brown, and this channel it gives some nice visualizations of this type of concept. So you can go ahead and watch this channel to get some good animated explanations of these concepts. So is this link visible to all? Yes, I pasted the link in the chat. So let's see how this MLE and MAP this sort of events occur. So let us take an example. Let us take this simple example. Let us take this example. How the posterior probability changes when your likelihood and your prior changes. So these you can get this example at this link. I'm sharing the link in this chat. So you saw in Bayes' theorem, right? So you have this likelihood, you have this prior, and using the likelihood and prior, you get the posterior distribution. So here, so suppose your prior is this black curve, right? So this is your prior probability distribution, and this blue one is your likelihood function that has been given. And using this prior and likelihood, you want to compute or estimate the posterior distribution. So let's see how the posterior changes as the prior and the as the prior or the likelihood changes. So this red one is the posterior. So see the as the prior. So we know that the posterior is a multiplication of this likelihood and the prior probabilities that have been given. So if we change the prior, the posterior also changes. So as you can see, the prior changes to normal, the posterior also moves. So similarly, the estimate of the posterior will also move. So this is how the prior and the likelihood changes the posterior distribution. Okay, what about this likelihood explanation? Okay, so suppose that I give you a data set, and suppose the data set has say 100 points, and I want you to answer me the question that what is the likelihood that this distribution comes from, or these data point, these 100 data points comes from a given probability distribution. So that means that you will say that you want to say how likely these data points come from a certain probability distribution. So suppose you take the point one, what is the probability that this comes from a comes from a distribution D. So you will have some P of x1 according to the distribution. Then you will take x2. So what is the probability that x2 comes from this distribution? So that is your px2. So in this way you will multiply p of x1 and p of x2 and p of x3. So this will give you a function, and this is what is called as a likelihood function. So in a sense it says that given some data points and given some distribution, what is the likelihood that this comes from this distribution. Is that concept clear? Yes, you have to be clear with the concepts of conditional probability to study this Bayesian networks or this Bayesian way of thinking, because this whole concept of Bayesian thinking is based on your conditional probabilities. So you have to know what you have to be clear about these terms like mutual independence, yeah, conditional probability, and all those topics, likelihood, MAP, MLE. So some applications of Bayesian. So um, this Bayesian. So ma'am mentioned this hidden Markov model at the end of the lecture. So those type of algorithms are used for say climate prediction or maybe speech recognition. And for Bayesian, there are certain types of functions called Gaussian processes. So those things are actually those algorithms are used for applied for say yeah, you want to check what is the purity of your air, or mostly in climate predicting the climate changes, and maybe your financial stock markets and all those sort of applications. Question 983. The question 9 asks in collaborative filtering based recommendation, the items are recommended based on what? So yeah, so you have seen like I mentioned that collaborative filtering was based on similar users. So this is the basic definition of collaborative filtering, right? So suppose you have two users who use similar type of movies, and so you will obviously recommend the same type of movies to them. So that is the concept behind this collaborative filtering technique.
Can I ask one more question on that?
Yeah.
The similar items also we'll use it when the large number of users are there for collaborative
Yes.
filtering. Am I right?
So that is not collaborative filtering. That I think that has another name. But by definition of collaborative filtering, so you want to find similar users and you recommend similar items to similar users. So
Is it the collaborative filtering is two types, similar users, similar items? No, not like that.
no. For when we talk about collaborative filtering, we're talking about similar users. So for similar items, it is there is a different name. I'm not sure, but that is not actually collaborative filtering. So we want to find the collaborations between users. You can think of it like that. Similar users will get the same recommendations.
Okay. Thank you.
Excuse me, for Bayesian problem networks and all, where we have to refer? You have given one link, that is enough?
Oh, that link, it does not contain any text. This is just for to get an exam understanding of how this works. So if you want to read, let me check. So you can go to, so there is a PDF available in this link. This is a probabilistic machine learning book by Kevin Murphy from MIT. So you can go to this book and you can read up on those topics from these books.
In assignment, there are some problems given, almost problems only there. Can you solve any one example like that?
From which assignment?
Fourth assignment regarding Bayesian network.
Okay, let me, okay. Give me one. So which question do you have a doubt in? Is there any specific question that you want me to discuss?
In this,
So these assignments are basically the application of the Bayes theory. Once you can understand how to apply this Bayes theory, most of these answers can be solved. You just have to understand which is the prior probability that has been given and which is a likelihood function. And once you understand where to put those, this should be straightforward. I think most of the questions are application of this.
Hello.
Yes, hello.
Yes, this type of problem to be solved, the link you have given, no? Is it sufficient to understand?
Yeah, I think this probabilistic ML book should give you a good understanding of this Bayesian type of thinking. Yeah, it should be enough. And you have those examples also. So the assignment questions are mostly applying Bayes theorem. So it depends on how you understand the concepts of prior and likelihood. So once you have those understanding, I think you can solve those problems.
Okay. Can you explain that prior and likelihood?
Okay. So let me show you. So I showed this example of a librarian and farmer, right? So
Yes.
when I say prior, by prior I mean in the existing population that you have, what is the probability of different events happening? So suppose this population has 210 people. So what is the probability of farmers, which is 200 by 210, and what is the probability of librarians? So this is a prior probability. This is like you have some prior knowledge, what prior knowledge of certain events happening. Now when we say likelihood, so suppose when I say that these 10 people on this left hand side are librarians, out of these 10 people, what is the probability that your librarians say satisfy this description? So that is the likelihood of that. Yeah. So likelihood is basically your probability that your data points are given, data points belong to this distribution. Are the concepts clear?
Okay, you told that for prayer, that farmer 200 population divided by the overall population 210,
Yes.
right?
Yes.
And for likelihood, 10 librarian divided by 210.
No. Likelihood is like out of your 10, your like 4 people are satisfies the description.
Yeah.
So out of your small population,
Yes.
what is the population that belong to that? So like you can see here. So that is your likelihood.
Okay.
So
So when
this
the
is your
data is when the data considering is minimum, that is likelihood.
Not minimum. You can say that suppose you have different groupings of your data. So for likelihood, instead of looking at the whole population, you look at look at this. This is your Bayes theorem, right? This one is a Bayes theorem. So this PB is the prior for event B happening, and so suppose B says librarian. So here, when I say P of A given B, it means given that he is a librarian, what is the probability of A happening? So A is your, say, the description that is given. So this is your likelihood, and this is your prior. Is that okay? So likelihood is basically you are, instead of looking at the whole space, you give some condition that given this condition, what is the probability of my event happening? So that is your likelihood.
So here it is given Bayes theorem, and in that P of D given theta likelihood, P of theta prior, and P of D evidence, and this one is posterior, right?
Yes, the one you are predicting is the posterior. So in English, like we know that P of theta is some, say, knowledge that we have. Yes, am I audible? So P of theta or prior is the knowledge that you already have. P D of theta is the events of likelihood of those events occurring based on the knowledge that you have, and using those two information you want to compute your update your knowledge. So now what is your knowledge given that we observe this?
Sir, can you hear me?
Yes.
In week 3 assignment, question number 2, can you give some explanation, sir?
Week 3 question 2.
Yes, sir. Week 3 assignment, question number 2. It is related to KNN.
Yes. So yeah. So what happens when we vary the value of k, right? So suppose we are taking a large value of k. So in that case, obviously we will include. So suppose, yeah, let me. So suppose these are your points. Suppose you take a very large value of k, right? Suppose for this, suppose you are taking k equal to 4. So you will include four, four nearest neighbors. So here you can see that you are getting, for here, you are getting elements from different classes, right? Because you are taking a very large the very large radius, or yeah, very large k, for large k. And for say you have some noise in the data set, due to which uh, due to the noise, suppose we have some point here, so this point may, because of some noise, this point may be placed here, this point may be placed here. So ideally when you're taking one nearest neighbor, we should have taken this, but due to noise this x was placed here, so it will take this, which is also not correct. So it is very sensitive to noise. So that is why both of these uh, options will be true. So for large k, you can, there is a possibility that, so suppose I take k equal to 5, so it may take points from the other class also. And if for small, if you take k to be small and there is noise in the data, so it may include points which are not in the same class. So both of these are true. Is that clear?
Yes, sir. So to have a better accuracy, is it better to have a k value smaller?
No, that is not the case. So you will have to test with different values of k. It depends on the data that you have. So you test with different values of k, and you will find some k that where you get the best results. So you need to experiment with that.
Okay, sir. Sir, in the same week 3 assignment, sixth question, can you give some explanation, sir? Week 3.
So we are given the class. One and y1. So it says that you have a data point at x1, y1, and using Euclidean distance, you uh, perform a tree nearest neighbor. So, so you can see that three of its, so Euclidean distance is like, I hope you are aware of Euclidean distance, but it is basically if you have some points in 3D space. So this is your Euclidean distance. So suppose this is your point, say 1, 2, and this is your point, say I don't know 3, 4. Your distance between them is basically 3 minus 1 square plus 4 minus 2 square. So this is your Euclidean distance. This is a distance. So if you form a right triangle here, what is the distance between this and this? So in question number 6, you can see that if you think of a point that is at 1, 1, so three of its neighbors are positive, as you can see in the diagram. So that is why the new point will belong to the positive class, because maximum of the neighbors are positive. So that is the class that we assign to our test data point. Is that clear?
So we have to take the maximum distance of the data point, is it, sir?
Yes. So suppose we have this red box, and suppose we have this blue axis, and suppose now I have some points, say this one, and I do a three nearest neighbor of this, and suppose these are the three nearest neighbors. So here there are two blue points and three red. Sorry, there are two blue neighbors and one red neighbor. So this point will assign the class blue to this point because that is the maximum that is contained in this tree nearest neighbor set. Is that clear?
Yes, sir. Thank you.
Sir, is it audible, sir?
Yes, yes.
Actually, the week 3, whatever the slides shared with us, no.
Mm-hmm.
Last some 3 pages are a little bit confusing. Can you see once?
Okay, let me check.
We got the slides, no? 97 pages are there. In the last 3, picture that the question number 9 I asked, no?
Mm-hmm.
The page number 94.
Before, yes. Okay. Okay, so here they mention 2 types of collaborative filtering, right? Okay, so actually, when we talk about collaborative filtering, we actually talk about similarity of users in general sense. But here, yeah, they have also mentioned user item-based collaborative filtering. So
Yeah, that's what I got confused with this statement actually.
yeah, so by definition, it should only be user-based, but we may also have item because I'm not aware that item-based similarity is called collaborative filtering. So that is why, yeah, I was also not aware of this. So.
Okay, sir. But pure definition is basically user-based.
Yeah, true
User-based.
definition is user-based. Yes.
This some variation that we're using is for application point of view. Theoretically,
Yes,
it is other one is the right answer.
yes.
Okay. Yeah. Thank you.
Sir, for our final exam also, do we get the questions based on use case or problem solving?
So I cannot. I am not aware of that because we are not involved in forming these questions. So yeah, I'm not sure about that. I think it will be handled by the NPTEL team and the faculties. So I'm not sure what type of questions that will be there.
Okay, sir. In week 3 assignment, can you give some explanation for 8th question regarding to PCA?
Eighth question.
Yes, sir. 8th question.
So when we talk about the regularization, regularization means how much, in some sense, how much you want to control your model that some machine learning algorithm is learning. So when we have a higher, so suppose we are performing a PCA with higher value of k, that means you are keeping almost all of the features of the data set intact. So that means you do not want to place much constraint on your model. That means you do not have much control on your model. So in that sense, you do not have a high regularization. You only have some quantity of regularization. So your model will perform as if there is no regularization if k is exactly equal to the number of data points. So if you decrease k more and more, you are saying that you are using only a small amount of features. That means there is more regularization because you do not have much data available to work on. You are preserving only the very the data which has the most variance. But yeah, as you increase k, your regularization decreases because you are using more and more of the information, even redundant information. So that is the meaning of the that is the explanation for this question.
Sir, actually, K is the subset of the given dimension. No?
K is the, suppose you have some data of say 100 dimensions, and your k is something less than 100, say 10 dimension. Instead of using 100 features, you are using only 10 features. K is a subset of the yeah, dimensions.
So when our K value is increases, we could get the better regularization. Is it so, no, sir?
Yes, if k increases, that means you are giving more and more information, right? Like you almost have your, so if k is equal to 100, you have your exact data. There is no loss of information. If you decrease k, there is some loss of information, due to which your model will be regularized to learn only the most important information. But if you increase k, your loss of information decreases. That is, you have more information, so your model will be less regularized in that case.
Okay. Sir, in the same week 3 assignment, 13th question, we have multiples of graphs.
Yes.
They have given the options as 1 less than 2, 3, 4, and again another set of options 7, 6, 5, 4. Can I know that value represents whether the number of plots which is in the graph or any other values?
Oh, these are indexes of the plots. So first plot, second plot, third plot, and so on. and by comparison they are measuring the this correlation campaign. So if it is almost linear, it means you have very high correlation. If it is less than linear, you have somewhat less correlation. Also, if a slope is like negative slope, that means you have inverse correlation. So like this.
They have given the answer as a second choice. That is 1 greater than 2, greater than 3, 4. How? I could not get it. What
So
is that? As you said,
you can
explanation I can understand, but based on the choice, I could not relate to that.
so your graph one is almost like a straight line, right? So this has a very high correlation. The graph two is
So it is
slightly
like
more. Uh-huh.
number. Is it so, sir?
Yeah, can you repeat?
Number 1, 2, 3 represents the graph number.
These are the graph numbers, yes.
Okay.
And we're measuring the correlation coefficients in these graphs. So if it is like a straight line, it has the highest correlation. And if it is not so straight, your correlation decreases. So it is like if you're increasing x, your y will increase in the same amount. So that means it is like very highly correlated. And if you're increasing an x by say 10 times, your y will also increase by 10 times or 100 times. So then it is highly correlated. Or if it happens, if you're increasing x 10 times, your y only increases by say 5 times, it is less correlated than the first example. So that's how we measure this correlation.
Okay, sir. Can you give some explanation of LDA?
So, so we saw that for PCA, what we did was we were reducing the dimension of the data. So if our data was spread like this, so we find the direction which maximizes the variance of the data, and we project the points onto this line. So this was our PCA. So now instead of plotting these points on 2D, you just plot these points on this one dimension line. So you are reducing the dimensions. But suppose that you also have some points like this. So this will also be mapped to this one dimensional line. So suppose I will draw it like this. Suppose this is your principal component, and you have points which are like this, and some blue points in between. So you cannot separate there, you cannot draw some line which separates the red point and blue point, because while this preserves the variance in the data, this does not contain the information of the class of the data. So ideally we would want some direction which reduces your dimensionality, and at the same time also preserve your class information. So that is what LDA does. So suppose if we take this example, suppose we project these examples on this line. So in that case, your red points will be projected to these points, and your blue points will be projected to these points. So these dots are your blue points, these are blue points. So if you look at this, so it will be like your blue points are on one direction and red points are in the other direction. So in this case, you can easily find some line which separates the blue points and the red points. So that is what the LDA does. It preserves the class information. So it maximizes. So suppose this is the mean of these, or this is the average of the blue points, this is the average of the red points. It tries to maximize the distance between the means of different classes, and at the same time it tries to minimize the distance of these points from their corresponding means. So if you do solve some problem which satisfies these conditions, you'll get this type of projection, and this is an LDA. Is it clear?
Yes, sir. So actually your LDA is also going to extract some features.
Yeah, it is also, it will
As
also
PCA,
reduce your future dimension. Yes, and at the
in
same
PCA
time
we
it,
proceed with eigenvalues and eigenvector, but here based on the average of the mean, we are proceeding with LDA. Is it so?
yes, this helps in preserving your class information.
So this is for a single class.
This is for two classes. This is your blue class, this is your red class.
Okay. So same thing, both PCA and LDA can also go for the multi classes for more than two classes.
Yeah, you can have that. So on one dimension you can, so here on one line you can separate two classes. So for three classes we'll require one more line. So because we cannot separate three classes on a straight line, right? We can separate three classes on two dimension. Similarly, you can separate four classes on three dimension, and so on. So you need that much of LDA components.
Is there any metrics to find the accuracy between this PCA and LDA?
So in PCA, you have something called the reconstruction loss. Suppose you have some data point X and some data set X, and you have some other data sets, say M. So M is your data set which has low dimensionality than X, and you want to compute the loss between, what is the difference between these two data sets in some algorithm. So that is called the reconstruction loss. How much information is lost due to reducing the dimensionality of the data. So that is how we, so lower the loss. So if loss is exactly 0, that means we are preserving all the information. The lower the loss, the better your reconstruction.
Reconstruction law can be proceeded for both, is it so?
Yeah, using
LDA
both
as well as
PCA.
PCA.
Yes.
Okay, sir. Thank you.
If there are no more questions, we can end this session. If there are no more questions, thank you.